Hi, so let's start here. Take some time to change the track, reset button. Okay, so they did update this a little, so it may look a little bit different. Let's see here. There we go. So, kinetic and potential energy, reset to the standard half pipe. Okay, so watch how the skater's kinetic and potential energy changes as the skater descends. Explain what happens to the total energy. Okay, so here we go. Here's the total energy. Here's the kinetic and potential energy as the skater descends and ascends. And over here is the pie chart. So let's try it with a different skater. This skater has this mass of 60 kilograms. Does this change the mass? Okay, let me just change the mass then. Let's try a skater with 25 kilograms. How does that change things? And watch how the energies over here change as, let's go back to 50 kilograms. There we go. So watch how the energy changes as, let's say, the mass decreases, whereas the mass increases. So that should give you enough information to answer that. Describe any changes to the bar graphs you see when you change skaters. In the old version, when you change skaters, it changed the mass also. In this one, you have to actually change the mass. Let's go back to 50. There we go. Pie chart and energy. There we go. So, okay, so we changed the mass. That's the equivalent of the question change skaters. Show grid checkbox. Grab the track, set the bottom at 0 height. Show the grid. The bottom is already at 0 height, so we're good there. Select the default. Okay, we're going to change this to 75 kilogram skater and set him at 5 meters. So let's make him 75 and grab the skater, and 5 meters is right there. Okay. How much does he have it? There we go. For this, you will have to calculate. If you remember, the potential energy is equal to mgh, so you will need to calculate it. Okay, so we got 5 meters. Um, if it, how much does it have at 5 meters? Kinetic energy has at 0 meters. That we should be able to answer. If a 20 kilogram skater started at 10 meters on Earth, let's make them 10. Okay, so 10. He's 20 kilograms. So let's make it 20 kilograms. And it's not going to let us start at 10 meters. So we go here, grid. The most we're going to be able to do here is 8 meters, it looks like. So let's do here. And okay, so now again, you will be able to calculate 20 kilogram skater at 10 meters. You'll be able to do that with the formula for potential energy. Is it up here? Right here. Here's your formula for potential energy. And that's the same formula you're going to use up here also. So uh, 10 milligrams, how much you start a skate at 10 meters. I'm only at 8 meters here, but you can do the calculation for 10 meters. And the trend between kinetic and potential energy is going to be the same. It's just going to be a little bit more total energy. And so you should be able to answer this now. So let's try to create this path. Let's see if we're successful. Let's reset it. Let's see what it looks like again. Okay, so and it goes up higher. Here it goes. So let's hit something like that. Okay, start on the left side and observe. I'm gonna make that a little bit like that. Okay, so start our skater there. I'm going to show the energy in the pie chart just so you can see it. I'll give you a few seconds here to observe. Okay, so does the skater have enough energy to make it all the way on the right side? Why or why not? See, and just out of curiosity, let's see if we started over here. See how much energy, total energy is right here? Let's see if we start right here, what happens to our skater. Maybe that'll help you with this a little bit. Okay, but if we start our skater here, there you go. So you should be able to answer that now. Left on the following path. You don't have to recreate this one. From answering the questions before, you should be able to answer this. Because it does not, here it's not asking you to actually calculate it, just so like you have point A, B, C, D, and E, it's asking you to give those letters. Potential energy, this doesn't require. Okay. Okay, so here. Okay, the gravity on the moon is 1.6 meters per second squared. So let's go back to here, where we have our pie chart. And let's reset it back. There we go. Now, you can affect gravity here. So let's just, for comparison, let's say the acceleration due to gravity on Earth is 9.8 meters per second square. The acceleration due to gravity, that's our g here, on the moon is 1.6 meters per second square. So let's reduce the gravity here. And how does that affect the total energy? Maybe you didn't see that. Okay. Let me do this so you can watch it more carefully. So here we are on Earth, right here. Look at the total energy, so on and so forth. Now, when we reduce the gravity, oops. So let's say we're on the moon here. How does that affect the kinetic energy, the total energy, and the potential energy when we reduce the gravity? And all you're doing is see the potential energy is equal to mgh. We're reducing this g. So how does that affect the energy? By comparison, uh, the gravity on Jupiter is 26 meters per second square acceleration. So that's like here. So how does that affect our total energy, the kinetic energy, and the potential energy when the acceleration due to gravity is much higher? Okay. There we go. Does this agree with the predictions you made in Q7? There you go. How high must the 20 kilogram skater? Okay, this is just a calculation. You're going to use the formula up here, and you're finding h, the height. Total energy, that's a calculation. You can use the same formula, but you're looking for energy this time. Again, this is essentially a similar calculation to Q11. You're looking for height again. Now, when you change the amount of friction, there we go. So let's reset all of this back. Put our skater here. And this time we're going to add friction. Ready? So right now there's friction none. So watch how this changes. I want you to look at the energy and the pie chart when we add some friction in. Ready? Now, what this is asking is, does the total energy change? without friction. Look at the total energy, it's right there. You see that? Except it's shifting between kinetic and potential energy. Now I'm going to add friction. Does the total energy change? And describe what's happening to the energy here. And so that should help you answer if the law of conservation of energy is still being observed. Law of conservation of energy is neither created nor destroyed. There you go.